Welcome back. In the previous videos, we saw our forward model of logistic regression. We also saw how we could use it in order to simulate the OR gate, NOR gate, etc. And during all these cases, what we were doing is we were sort of guessing for weights. Without actually doing the gradient descent, sort of by a heuristic sort of rule of thumb guessing, we figured out some weights for which we could replicate the OR gate. Now obviously that happened well because we had only 4 data points and we just had to fit a classifying line between those 4 data points. In general, of course, it is not really possible to just guess for a good line, which is why we will look at how to calculate the gradient of the logistic regression, which will complete our loop. So remember, for logistic regression we are dealing with input nodes as usual x1, x2, x3, and we can have our usual bias unit sitting there. We have one output. Why only one output? Because this is binary classification. So the output is either going to be 1 or 0, or in our prediction case y hat, which lies between 0 and 1, and all these put together, let us split it into 2. We have our summation and then we have our sigmoid. This gives us y hat. At the end of the summation, whatever we get is z, and at the end of the sigmoid whatever we get is y hat. Now the weights which we do not know are here, W0, W1, W2, W3 and so on and so forth up till Wn. Remember, just like in linear regression, you could choose x1, x2 to be x1 square, x3 to be x1, x2, etc., etc. So you can choose nonlinear features as well. Okay, this is just as a reminder. Okay, so what is missing in this picture? We do not know these w's, this is just the forward model, and we follow our usual procedure. You have the forward model, you guess for the w's, you get a y hat, from the y hat you get a j, from the j you feed back using del j del w, and through gradient descent or some version of gradient descent to calculate all the an improved guess for the w's. So what is missing here is of course this del j del w. So I am going to write the whole thing in a vectorial representation. You have x vector, it runs through a sigma using a w, then through a non-linearity through a sigmoid you get y hat, okay, and this y hat is what gives you j. So just for simplicity or clarity, I am going to represent this slightly differently. Let us say x vector, I will show the sigma here, I run it through w, I get z. I run z through a non-linearity and I get y hat, from y hat I get j, and what I want is del j del w vector. Okay. The question is, what is the expression for del j del w vector? Now this is fairly straightforward, let us trace this back. Del j del w vector equal to del j del y hat times del y hat del z times del z del w vector. So this is sort of the dependency. j changes because w changes. Why? Because j changes due to changes in y hat, y hat changes due to changes in z, and z changes due to changes in w. In another way, when I perturb w, it will perturb z, which will perturb y, which will perturb j. So, that is what we are chasing down here. This is essentially the chain rule. When we come to neural networks, you will see that it is exactly the same idea which is applied for what is called a backpropagation algorithm. Okay. So, let us now calculate the expression for this. So, let us look at each of these terms individually. Okay. First, what was j? J, if you recall, I had written as summation of y ln y hat plus 1 minus y ln 1 minus y hat. Okay. I am going to put an I here and I equal to 1 to m. Now, what is this I equal to 1 to m? This is very similar to what we did. In fact, it is the same to what we did when we were doing linear regression. Recall, suppose you have x vector as in the example that we have shown here, and you have multiple examples or multiple data points. Okay. So, for the first data point, x vector was x1, x2 up till xn, where you have n features, and I am going to put a superscript 1 to say that this is the first set of data points. In the case of the OR example, we had 4 such data points. Okay. So, you had an x1 1, x2 1, which was 0 0 in that case. You similarly have x1 2, x2 2, xn 2, and we could have m such examples very similar to the multiple linear regression example that we did. Now, we have the ground truth, and since this is binary classification, ground truth here is y1 will be either 0 or 1, y2 will be either 0 or 1, and you have ym. Then we have our y hat, which is our prediction, which is h of x given the parameters w. So, you are going to have y hat 1, y hat 2 up till y hat m. Finally, I am going to introduce something new just for clarity. I can have j I. What is that? This is the loss just due to the ith example. Okay. So, going back here, suppose you had 4 points, okay, and let us say this value was 1. This was y, and y hat was let us say 0.8. The very fact that y hat and y differed will give you some amount of loss. So, j I is just the loss in the ith example. Okay. So, you will have j 1, j 2 up till j m. Okay. Even in linear regression, you can see if you have a line and you have multiple points, the loss for each one of those points will be denoted as j I. So, coming back here, all I am writing is j is the summation of all the binary entropy losses from each individual data point. Okay. So, it is simply the summation of all individual losses. Okay. So, suppose I want del j del w, this is also going to be, actually I will remove the minus, let us include the minus within the j I. This is del j I del w vector. Okay. So, we have this del j I del w vector is equal to del j I del y hat del y hat del z del z del w vector. Okay. Technically speaking, this is y I. Okay. For now, I am going to drop the I in the future expressions and we will just sum it back just for clarity of notation. Let us look at this term first. Okay. So, I am going to drop the I as I said. J is minus y ln y hat plus 1 minus y ln 1 minus y hat. Notice that the derivative is with respect to y hat, because that is what depends on w. Y is fixed, y is what we gave, y are the labels that we gave, y hat is the parameter that y hat is the hypothesis function that we get out of the prediction using our parameter w. So, what is del j del y hat? Del j del y hat, this term is minus y by y hat minus 1 minus y by 1 minus y hat. Okay. So, we have that expression. What about del y hat del z? Del y hat del z is, remember, y hat is simply sigmoid of z. Okay. That is how we calculated it. If you come here to this picture, y hat was calculated as g of z or sigmoid of z. Okay. Now, luckily in a previous video we already calculated this derivative. This was simply sigmoid of z times 1 minus sigmoid of z, which is the same as y hat times 1 minus y hat. Okay. So, if you put it together, then you get del j del y hat multiplied by del y hat del z is equal to minus y over y hat minus 1 minus y over 1 minus y hat times y hat times 1 minus y hat, and if you calculate this, you get a very simple expression which is simply minus y minus y hat. Okay. Please check this for yourself. So, we can call this expression even del j del z by the chain rule. Del j del z is equal to minus y minus y hat. This is simply the negative of the error. Okay. That is, if you made a prediction y hat and the ground truth was y, del j del z is simply minus y minus y hat. We have one other term left in this expression, which is del z del w hat. Okay. Remember, z was w vector dotted with x, where w vector includes w naught. Okay. This was this expression we saw the augmented w and the augmented x, x now includes 1 x 1 up till x n. Okay. So, this can be written as w transpose x also as x transpose w. We saw in the linear algebra videos that in such a case, when you have del z del w where z is equal to x transpose w, this means del z del w is simply equal to x vector. You can do this via algebra also, or you could do this using the notation that I used in week 1 of this course. So, if you put these two together, you get del j del w equal to del j del z multiplied by del z del w. This is equal to minus y minus y hat multiplying x vector, okay, which is minus the error multiplied by the input. Now, there are several noteworthy things here, I will go over them one by one. First, I will write the general expression. This of course is del j I del w. Okay. So, if I look at del j del w, this is going to be summation from I equal to 1 to m of y I minus y hat I multiplied by x vector. So, for example, if you wanted del j del w naught, you will get y I minus y hat I multiplied by x naught, which is simply 1. So on and so forth. For each component of w, you take the corresponding component of x. This is a vector, that is also a vector. Okay. So, this expression is for logistic regression with binary cross entropy. Okay. Now, some of you might recall that we had exactly the same expression except for a factor of 1 by m, which we can either include or not, exactly the same as linear regression with least squares. So, please refer back to your notes and check whether this is true or not. So, this is actually remarkable. You get the same expression for the gradient for logistic regression with binary cross entropy as you get with linear regression with least squares. This is true even when you start including regularization. So, when you include the regularization of, as Dr. Ganapathy had shown earlier, if you include regularization of lambda norm of w square, that would also add normally within logistic regression also. The same thing holds true even for neural networks. So, but the expression is actually exactly the same. This does not mean that the j is the same. Remember that this y hat means different things for linear regression and for logistic regression. For linear regression, y hat was simply w transpose x. For logistic regression, y hat is now sigmoid of w transpose x. So, please do remember that. The second noteworthy thing here, which is not obvious, is that for logistic regression, the loss function j is not convex. Okay. So, I will not go into what a convex set means, but you can think when we had least squares, generally the cost function will look simply like a paraboloid. Okay. So, this is what is called a convex function, where you have only one minima. Okay. The most important thing for us to know is that the minimum is in general not unique. We can understand this kind of intuitively too. For example, we were trying to classify this set. Now, notice when we were doing the OR gate, we chose one line which was like this, but there is no reason to choose only this line. Even this line functions as a classifying line, this line functions as a classifying line. So, there are many possible classifying lines. So, logistic regression does not give unique solutions. So, in our whole process, depending on which w you start with, remember that our initial sets of weights we were guessing randomly. So, the random guess, depending on where it is, you might get one classifying line or the other. Okay. So, logistic regression actually depends on your initial conditions, which classifying line you get. Okay. So, that is an important constraint. This is also a problem with neural networks. It will never necessarily, does not necessarily give the global optimum. So, in gradient descent, let us say you have two local minima. At one place your gradient is 0, at another place also your gradient is 0. For example, if you have something of this sort, it is quite possible that your gradient descent comes here and gets stuck, okay, and does not move from there, rather than come here, which would actually be the global optimum. So, this is true whether it is logistic regression or whether it is neural networks, which we will see shortly in future videos. But for linear regression, typically if you converge, you will converge to only the global optimum, because there is only one optimum, because it is a convex function. So, this is important for you to remember, that logistic regression does not necessarily deal with convex loss functions. So, in order to sort of solidify your understanding of the logistic regression process, let us now look at a code which does logistic regression. You will see that this is just a small modification of the linear regression code that we had already used earlier. We had written a generalized linear regression code. So, since the gradient expression for logistic regression is practically indistinguishable from that of linear regression, we will use the same code in order to do logistic regression. I will take the simple example of the OR gate, and in this case, so we will start with once again our example 1, 2, 3, 4, we will treat it as 4 data points or and x vector which was 0 0, 0 1, 1 0, 1 1, and we have our ground truth which was 0 1 1 1, and we put the same model as before, a summation followed by a sigmoid gives us y hat after taking in x. Now, what I will also be doing is, both in the code which you will notice as well as in the expression here, we will write it as if we are writing vector expressions, just to tell you how that works. So, if you have x 1, x 2 and x naught here, which is just 1, we sum these 3 up, w naught, w 1, w 2, okay. What comes out is y hat after you put sigmoid and g. You can write this as z, which is the intermediate output of this, z is equal to w dot x. Okay. Remember, this w also includes the w naught, which is the bias term, and x also includes x naught, okay, and y hat is equal to g of z. This would be the vectorized expression, and this is what lets us write a general code with great amount of ease, because suppose I decide to use other nonlinear features. For example, you saw the XOR gate example. In the XOR gate example, suppose you wanted to include x 1 square, x 2 square, etc., you could simply include extra features x 3, x 4, and that would, logistic regression would still work as it is. Okay. So, we will look at a vectorized code for this in the next video, which would be the code. Thank you.